And this is joint work with my wonderful collaborators, Lakshman and Shun.
You pronounce it, the Q is something like
Shun.
I see, okay.
I guess she also goes by Quan.
Okay.
All right. So yeah, first let's define the K-core decomposition problem. So the input is a undirected graph, and we define a K-core of the graph to be a subset of the nodes, which such that the induced degree of each of the vertices is at least K. So for example, this is the 3 core of the graph because in these 4 nodes, each of them have degree 3. And then the core number is the maximum K such that there exists a K core containing that vertex. And the core number of a vertex. And for example, the core number of all of these vertices will be 3. And now the K core decomposition problem asks us to compute the core numbers of all of the vertices. And because we are working under differential privacy, we need some notion of approximation. So our goal will be to output alpha beta approximate core numbers, which are just the approximate core numbers with alpha multiplicative error and beta additive error. And our main result will be that show that under differential privacy, with for any eta greater than 0, we can show that we can give an algorithm which outputs 1 plus eta order log n approximate core numbers. And this improves upon the best known results. So to better understand the K-core decomposition problem, let's go over a simple peeling algorithm for it, which is probably folklore. I don't know the citation for it. So in order to output all the core numbers, it suffices to find a maximal K-core of the graph for each K. And then you basically just, for every vertex, you just look at each K and then find the largest K that such that it's still in the K-core, and that will be its core number. So to do that, we start with this candidate set for the K-core of the graph, V of K. And recall that the K-core contains vertices such that the induced degree in the K-core is at least K. So I guess the natural idea is to peel off the vertices that have induced degree less than K. You just keep doing that until there are no more of them. So that's exactly what we do for each node in the candidate core V of K. You look at the degree in the induced subgraph, and if the induced degree is less than K, you mark it to be removed. And then after this for loop, you remove it, and then you repeat this until there are no more nodes to be removed, or we can also say that V of K, I guess, converges. Okay. Let's analyze the simple peeling algorithm because it ends up forming the basis for our private algorithm as well. So suppose that the induced degree is always at least K in this V of K throughout the entire algorithm. Then it's pretty clear that, first of all, this vertex V is in V of K at the end because it never gets peeled off. And this implies that this also implies that V of K will be a K-core in the graph, because at the end, all of the vertices have induced degree at least K, which is the definition of K-core. And as a result, the core numbers of V will all be at least K. Now, conversely, suppose that the core number is at least K. So we've shown here that the V of K is indeed a K-core. We want to show that's a maximal one. So suppose that the core number is at least K. We want all of these vertices to be contained in V of K. We want to show that. So to see that, because the core number of V is at least K, there exists some K-core which V is contained in. And for this K-core, we know that none of the vertices are ever peeled off because they always have induced degrees at least K. There's always at least K numbers in at least that K-core. So it never gets peeled, so that as a result, V will remain in this candidate V of K at the end, which implies that indeed V of K at convergence is a maximal K core. So I hope people understood this, because for the rest of it, I'll basically be having like some multiplicative error and some additive error on top of this algorithm. And I'll just be hand waving and saying, if you just follow this analysis, you get the multiplicative and additive approximations to the K core values as well. Terrific. So now that we've defined the K core decomposition problem and got some intuition for it, let's also define the other part of the problem we're working on, differential privacy. So differential privacy is this standard notion of privacy that people like giving nowadays. And on graphs, it's called edge differential privacy. The differential privacy is defined in terms of neighboring databases, or in our case, neighboring graphs. We say two graphs are neighbors if they differ by a single edge. And differential privacies guarantee an algorithm is said to be differentially private if for every two graphs that differ by a single edge, but for every pair of neighboring graphs, the output of the algorithm is similar in distribution when the algorithm is run on G and G prime. So for our definition of similar distribution, this formula here, but to give some intuition for it, we should think about epsilon as being a pretty small number. So each of the epsilon is about 1 plus epsilon. The probability distribution when the algorithm is run on G and the probability distribution that the algorithm is run on G prime are similar up to this like 1 plus epsilon factor. And that's what differential privacy guarantees. To give some intuition for why that's a nice privacy guarantee. So consider an adversary that's looking at the output of the algorithm. So the guarantee of differential privacy is that this adversary can't really tell the difference about the graph if a single edge exists or not. So they can't tell that the existence of a single edge. And this is because the output of the algorithm is very similar in distribution, so they don't gain any new information whether or not a single edge is added or removed. Yeah, that's the hand wavy definition of differential privacy. So for the talk, we won't need to know too much about differential privacy. I'll just go over some basic things that we use. And for the rest of it, I guess you can read about it in your own time. So the first nice property about differential privacy is the composition theorem. The composition theorem essentially says that if you have one algorithm that's epsilon 1 dp, another algorithm that's epsilon 2 dp, and you combine the two, or if you look at the output of both of the algorithms, you run both of them, then the resulting algorithm is epsilon 1 plus epsilon 2 dp. And
so you by running both, you mean one calls the other, right? It's
no,
program composition.
just run one and then run the other.
Or run one on the output of the other.
Yeah.
Okay.
As Arvind mentioned, if this composition theorem applies even when the algorithm is chosen adaptively. So you run A1 first, you look at the output of it, then you can choose A2 depending on the output of A1. And even in this scenario, this adaptive setting, you can still get this composition theorem. And this is nice for DP, especially in algorithm design, because you can analyze different parts of the algorithm separately. And then if you say each part is epsilon DP, and then there's like 20 parts, you can get some differential privacy guarantee for the entire algorithm as well. Okay. And I'll also mention the simplest, I guess, most canonical example of a differentially private mechanism is the Laplace mechanism. So when you're outputting some number, and that depends on some private information, I guess in order to guarantee privacy, I think the first reaction for most people is to add noise. And as the name suggests, the Laplace mechanism adds Laplace noise. So the question is, how much noise do you need to add to guarantee differential privacy? Okay, so to answer this, we need to find the L1 sensitivity of the function. So f, which is the vector valued function, is the question we want to answer while guaranteeing privacy. And the L1 sensitivity is basically how much the function can change in L1 distance between neighboring databases. So xsim x5 just means that the two databases are neighboring. In our case, it means that they differ by the graphs differ by a single edge. And the L1 sensitivity is just how much this vector changes. And then the Laplace mechanism adds Laplace noise to each of the coordinates of the function f. And the Laplace noise is scaled proportional to the L1 sensitivity. And I think this is at least somewhat intuitive, because if the function changes more on neighboring, because differential privacy wants to guarantee privacy with respect to neighboring data sets. They don't want the output to change too much. So if the output can change a lot in L1 sensitivity between two neighboring data sets, it's natural that you want to add more noise to like mask that change. And that's why the Laplace mechanism scales with.
Can you remind us of the density of the Laplace distribution?
It's like a two-sided exponential distribution. So I think the only thing I'll be using here is that the tails decay exponentially. So with high
The
probability,
density is like e to the minus the absolute value of x, basically.
divided by the scale, right? Yeah, okay. And in order to convince you that the Laplace mechanism is epsilon dp, I want to bring your attention to this figure. You stare at it really hard. I hope you can be convinced that like this difference should be pretty small. So it should be about e to the epsilon. And yeah, I guess that's as much of a proof as I'll be giving probably during this talk. But yeah, the Laplace mechanism is epsilon dp. So given the Laplace mechanism, so remember in the K-core decomposition problem, we want to output core numbers for each vertex. So that's really just a vector of core numbers if you identify the vertices with the first n and natural numbers. So I guess the first natural thing to do is try to apply the Laplace mechanism directly. And in order to do that, we have to compute the L1 sensitivity of the vector of core numbers in order to apply it. So the problem with this approach is that it turns out the L1 sensitivity of the core number vector is theta n. And to illustrate that, to give an example proving that, let's look at the cycle of length n. In this cycle, you can clearly see that all of these have degree 2. So the core numbers of each vertex, the core number of each vertex is 2. Now let's consider this graph when we remove a single edge. It becomes this line graph. And it turns out that all of the core numbers here become 1. So should I convince you guys that that's true? Yeah, let's convince you guys. So it's pretty clear that this one is 1, right? So that means this vertex can't be in the 2 core. So now because this vertex isn't in the 2 core, we can like essentially ignore it. Like you can think about this as running the algorithm. We peel it off. And so now this vertex only has degree 1. And now you just like go through it the entire time, and now all of the vertices can't be in the 2 core. It's clearly in the 1 core. So the core number is 1. So if you look at these two, each of the vertices, their core numbers differ by 1. So the entire vector has L1 sensitivity n. And now if you run the Laplace mechanism on this, you'll have like theta n additive error, tilde theta n additive error. And in the beginning, I promised you guys that I'd get you additive log n error. So that's why this will not suffice. Okay. So in this first attempt, the main problem was that the sensitivity was high. So I guess the natural thing is.
Excuse me, George. So you didn't relate the accuracy to the amount of noise. Can you just say, okay, so in this case, the noise you have to add, the mean for the Laplace distribution should be n over epsilon, right?
Yes.
So what, can you say then what it implies for the accuracy?
Yeah, okay. So, yeah, because you have to add noise that's proportional to n. If you want to get high probability bounds or even expectation bounds, the expected absolute error or the expected maximum error for all of the coordinates will be n log n. Yeah, because you have to use the union bound, I guess.
It'll be O of n, but yeah, but still that's too high. If the mean is already O of n, the probability is more than twice that is exponentially small, right?
Oh, okay. In my mind, high probability is 1 minus 1 over n.
No, but if a random variable is mean c times n, the probability that it's more than 2cn for something like Laplace is exponentially small in n, right? So if you're doing a union bound over n vertices, I mean, it's a minor point I'm making.
No,
it's not
because the distribution is e, like it scales with the difference over the sensitivity. So in order to get high probability bounds, you need like an extra log n factor.
Thanks.
Yeah. So, but okay, for the sake of us, if you have L1 sensitivity, something, in order to get high probability bounds and for union bounds to work throughout the whole algorithm, just imagine that the error will be increased by a factor of log n. Okay, so for a second attempt, in the first attempt, the main problem was that the sensitivity was too high. So a natural thing that has low sensitivity is the degree or the induced degree of a vector or the vector of induced degrees in the graph. Because if you change a single edge, that can only affect 2 vertices. And as a result, the sensitivity is only 2, which is much better than n. And if you remember our simple peeling algorithm, it only used the fact that it only used information about the graph through the degrees of the vertices or the induced degrees. So a natural thing is to take our peeling algorithm, and whenever you want to use the degree vector or the induced degree vector, you just add Laplace noise to that degree vector. And that guarantees differential privacy for this. Unfortunately, this still runs into some problems. So the problem is that there's too much composition. So if you remember when I talked about the composition theorem, I said if something is epsilon 1 dp, something's epsilon 2 dp, running them in sequence gives you epsilon 1 plus epsilon 2. I guess by induction, if you have n mechanisms that you're running sequentially, then the resulting mechanism will be n epsilon dp. So if you look at this algorithm, even though this step where you have to use the graph is epsilon dp, we need this for loop here, which runs n times. And also this while loop, do while loop, that in the worst case, it turns out to also need n rounds. And as a result, because we have these we have to apply the Laplace mechanism n squared times, this becomes n squared epsilon dp, which is actually even worse than just applying the Laplace mechanism directly. So this can kind of be fixed a little bit. So this first step at least can be fixed. So instead of looking at every k, you just increase it geometrically by 1 plus eta for some eta greater than 0 of your choosing. And now this will only have log n rounds of composition. And for the sake of us, I think we can essentially ignore all polylog factors. And the problem still lies here. This still has n rounds of composition. So now we have like n log n epsilon dp. So now this is just similarly as bad as the Laplace vector. So to summarize, in these 2 attempts, the first problem is that the sensitivity is too high. So when we add Laplace noise, it's bad. In the second attempt, we have too much composition, so we lose too much privacy, which just goes to the additive error. So let's look at some ideas from previous work by my co-authors and some others to address these 2 issues. So this is by Lakshman, Chen Xuan. Oof, I know this, give me a second. Sophia at Boston. One of these is Julian, one of them is Jessica Shi, and the last person's someone who's going to be coming to UMD to give a talk in like 10 days, Shang Bi. Yeah, cool, nice. So in their work, their main observation is that parallel algorithms are really nice for differential privacy. And the reason here is twofold. They address the two issues that we saw in our first two attempts. The first one is the low depth of the parallel algorithms means that we won't lose too much from composition. We'll only lose polylog factors, which we are willing to ignore using tilde notation. Another nice property is that parallel algorithms, at least on graphs, usually have this local nature. They only use local information about the graph for each node. So to convince you that this means that the sensitivities are usually low, let's look at our example again. When we consider the degree of a vertex, right? That's like the most local thing you can do. And that has sensitivity too. If instead you look at the k-core of the vertex, or the k-core vector and the degree vector of the vertex, that's like a more global thing. It's trying to capture global information about the graph. And that causes the sensitivity to be theta n. So with these two nice properties, they can show that some parallel algorithms for k-core can be used to give a 2 approximation with polylog n added there. So yeah, that's really neat. It definitely beats the two things I mentioned before. And our main goal to be, well, B2, improving this bound. Unfortunately, their ideas have this inherent barrier, at least right now, where parallel algorithms for k-core, there's nothing, it's not known how to do better than a 2 approximation. So in my first slide, I said that I wanted to get a 1 plus eta approximation instead of this 2 plus eta approximation. So using just parallel algorithms will not be enough. Or another approach will be to improve the parallel algorithms, and then we can discuss this again. So given this limitation, this parallel algorithm route is kind of broken, and we'll have to use better ideas, or at least new ideas. And thus comes the third attempt. So here it turns out that the second attempt was not that far from, I guess, the correct algorithm, or at least our algorithm. The main problem with that attempt was that this do-while loop has n iterations. So if you use composition on it directly to analyze it, that means you lose a factor of n. And yeah, what we want to do is to analyze this without using composition. We want to analyze it directly and claim that it's like something like 16 epsilon dp, or maybe 8. 16 epsilon dp. And yeah, if you just look at it, it's not that clear because you're running the Laplace mechanism n times. It's not clear that you can even show anything beyond n epsilon dp. So I'll first give some intuition for why you might think that this is possible. So for this intuition, let's focus on a single vertex. We have a threshold k. And what this algorithm is basically doing is it has this stream of queries, fi, which are the queries about the induced degrees of that vertex. And then we want to output an indicator answering whether or not this query is greater or is lower than the threshold. So some nice properties about this like abstract problem that we are essentially working with is that first, instead of outputting the true values of each of these queries about the induced degrees, we're only outputting the indicator variables. So we're giving less information, so we can hope that we can do better than just the naive analysis. Also, intuitively, only the queries that are close to the threshold should impact privacy. So differential privacy guarantees that when two things are neighboring, when one edge is added or removed, the output distribution doesn't change much. So if you're really far from the, let's say this is the threshold. Let's say this is the threshold, and this is your query value. No, wrong way.
Sorry, so what do you mean? I see, so the query is whether X is greater, the threshold is some T, and the question is if X is greater than or equal to T. Okay.
And yeah, if you're far from the threshold, okay, I don't know which hand I'm supposed to use, but one's the threshold, one's the value. If you're far from the threshold, then when a single edge is added or removed, you move a little bit, but you're still far from the threshold, so the output of your algorithm doesn't change. So as a result, intuitively, things far from the threshold shouldn't be causing problems for privacy. So hopefully this really hand-wavy intuition can convince you that maybe something better can be done. And it turns out, indeed, there is something better that can be done. You can give an epsilon dp algorithm with log and additive error. So what do I mean by additive error here? So our outputs are a sequence of indicators. And what I mean by additive error is, suppose that your query is really far from the threshold, like way higher than the threshold, then you never make a mistake. It's only when the query is really close to the threshold, you're within some log n of the threshold, that's the only scenario where your algorithm might make a mistake. So you only have like this log n error in answering this query.
Why exactly log n?
Why exactly log n?
Because we are log n.
It just turns out that it's log n, but we want to be close to the threshold because I think this is like a natural
It's just why it's
upper bound.
Why is there farther than log n? Like why specific?
Okay. Why specifically log n? So, okay, this is still with high probability. It's essentially some more fancy version of adding Laplace noise. And it's because, so there should be like a WHP with high probability here. And so when we're far away, we don't like get it completely for free. We still have to add noise, but it's just that the tail decays fast enough so that after log n, all the probabilities are low.
Oh.
So this intuition is not like completely correct. It doesn't not impact privacy, it just doesn't impact privacy as much. Okay. So let's say the sparse vector technique. It turns out to be remarkably similar to our attempt to. So you have this threshold, and for each query, you check if the query is greater than the threshold after adding noise to the query, adding Laplace noise. And you use that to decide if do you output above threshold or below threshold. The only difference is now you add noise to the threshold K as well. And in preparing for this talk, I wanted to give some intuition for why you also add noise to this K. After looking through Cynthia Dork's book on differential privacy and also Gautam's lectures, both of them said that this is just a technical trick in order to guarantee privacy. In the analysis, you write probabilities as two integrals, you manipulate those integrals really cleverly, and then somehow at the end it's epsilon dp, and it requires in the analysis that you add noise to the threshold. So unfortunately, I have no intuition to give you, so I will just need you to believe me that this algorithm is epsilon dp. Quite a tragedy. So if you guys believe me, now I can give the full algorithm, basically just using this.
Sorry, George, so did we go from the 2 plus eta to the 1 plus eta?
We will soon.
Okay.
Actually, yeah, in this next slide, actually. Very good timing. So using the sparse vector technique, we'll be able to give this full algorithm. So again, these threshold or K-core candidates, we increase it geometrically, by factor of 1 plus eta, or eta of your choosing. And okay, we still have this candidate set V of K that we want to peel the low degree vertices off of. So following the sparse vector technique, we add Laplace noise to the threshold and Laplace noise to the vector of induced degrees. And then if your noisy induced degree is less than the noisy threshold, you peel the vertex off, and you keep you keep doing this until V of k stops changing. But while you guys take in this algorithm, I'll just, I guess, talk a little bit. So in the sparse vector technique that I mentioned in the last slide, we were focusing on a single vertex. You know, we were looking at, okay, if the induced degree is higher, you say above threshold. If the induced degree is lower, you say below threshold. Right? But now we're kind of doing n of these at the same time because we're doing the sparse vector technique for all of the n vertices at the same time. So it's not immediately clear why this is allowed. So I'll start hand waving again. If you look at all of these n sparse vector techniques, if a single edge is added or removed, only 2 of them are affected because an edge is only incident on 2 vertices. So as a result, you really should only lose like a factor of 2 in the privacy instead of a factor of n when you do n of these sparse vector techniques. And this is also why the Laplace noise added here is 4 and 8. If you remember in the previous slide, it was 2 and 4. It's because of this factor of 2 loss. Yeah, this is a bit, in our paper, we essentially follow the proof of the sparse vector technique for this, which we call the multi-dimensional sparse vector technique. And I hope that's enough to convince you guys that this is still private with only constant factors of loss. Okay, now for an analysis of this. Arvin, this is your the 1 plus eta that you wanted. So for privacy, my 1 minute of hand waving a few seconds ago says that if you use the sparse vector technique or the multi-dimensional sparse vector technique, each iteration will be epsilon prime dp. And then because there are log n iterations, because we increase things geometrically by a factor of 1 plus eta, then the full algorithm is log n times epsilon prime dp, and we chose epsilon prime so that it's equal to epsilon. So we have epsilon dp for this algorithm. And for accuracy, I'll be even more hand waving. So for the geometric increasing thresholds by 1 plus eta factor, that intuitively loses a 1 plus eta multiplicative error when we compute the k-core values. And when we add Laplace noise, the Laplace noise with high probability is log squared n. So that loses an additive error of log squared n. And now I warned you guys about this like 30 minutes ago, that if we follow the original proof for the peeling algorithm, but now with these multiplicative and additive errors, it turns out that we can show that this is a 1 plus eta and log squared n approximation. So this is nice. This already improves the FOCS paper, which is always a good thing. But this isn't exactly what I promised you guys 30 minutes ago. I promised you guys 1 plus eta and then I'll order log n. I'm off by a log factor here. So we need to be even more clever. So to do this, we need to use this privacy amplification lemma and also some ideas in sublinear algorithms. So suppose you have this epsilon dp algorithm, but instead of running it directly, you first sample each edge with probability p, and then you run the algorithm. The question is what privacy guarantees can be set then? Can you improve the analysis? So yeah, so now you have a sampler before you run the epsilon dp algorithm. And if you were in Arvin's class last semester, you would have proven this in homework that the resulting mechanism is p times epsilon dp. And I think this is reasonably intuitive because in the sampler, you'll be adding extra noise. It will be harder for an adversary to identify whether or not you are in the your data is actually in the data set or in the graph. And as a result, you have improved privacy guarantees in this setting. Okay, I hope you guys believe me. Now we'll be using ideas from sublinear algorithms. So for sublinear algorithms for the k-core problem, if there's this very standard pipeline, what they do is they sample edges independently with probability p, so that so I guess we'll be basically sampling a sparse file for the k-core problem. And this is a safe space or runtime. And after that, they use turnoff bounds to argue that after you sample the edges independently, the k-core values will essentially just decrease by a factor of p by using turnoff bounds. And as a result, if you just multiply by 1 over p, then you can get a good estimate of the k-core values in the original graph. So for privacy, we'll basically follow that idea. We will sample the edges independently with probability p. We'll use turnoff bounds to estimate the k-core values in the original graph. And now the key is that we'll be using privacy amplification in order to improve the privacy analysis with the goal of saving this extra log n factor. Okay. So now we'll take the original algorithm and then add this sampling process in it and hope that this will be enough to improve the privacy analysis. So yeah, we still have this candidate set V of k. And now the key changes are we choose this P of k, the probability of sampling, so that P of k times the k-core value is greater than 6 log n. And this is just so that we can apply turnoff bounds nicely. And the tail will be e to the negative 6 log n, which is some big enough inverse polynomial so that we can use union bound whenever we want to. And now we sample each edge with probability pk. And now the remainder of the algorithm will be the same. You add Laplace noise using the sparse vector technique, and the only difference now is that you check if the noisy degree is and you compare the noisy degree with this decreased threshold pk times k tilde, and then after that you use turnoff bounds to argue that this threshold is like a correct one. Okay. So now, wait, actually go back. So I want to mention here that let's say we always set pk such that pk times k is equal to 6 log n, right? Since k is geometrically increasing, that means that p will be geometrically decreasing. And this is the key property we will need to get the improved privacy analysis, which I will show you now. So in the original algorithm that got log squared additive error, we said that each iteration is epsilon prime dp, and then there are log n iterations. So the full algorithm is log n times epsilon prime, which is epsilon dp. In the new algorithm, because we are doing the sampling, and then because of the privacy amplification lemma, each iteration, or iteration k, is pk times epsilon prime dp. So the full algorithm is some pk times epsilon prime dp. And the neat thing here is, as I mentioned before, pk forms a geometric series, or I guess a finite geometric sequence. And the sequence is bounded from above because these are probabilities. So as a result, we know that the sum of pk is at most a constant. This constant depends on eta, but it's a constant. So as a result, we can set epsilon prime to be epsilon over c for some constant c. So originally where we lost the log squared n is we had log n error and then over epsilon prime, and epsilon prime was epsilon over log n, so you have log squared error. Now since epsilon prime is epsilon over c, you only get c log n error. So you save by constants. And I'll hand wave the accuracy analysis again, but it's basically the same thing, but now you use turnoff bounds to argue that stuff concentrates nicely, and the k-core values are accurate up to some 1 plus eta factor. And then you choose eta to be eta over 2. Okay. So that concludes our results on the k-core problem, or k-core decomposition problem. And now I'll mention some other results we have in the paper. So basically, if you follow the same thing, you can also show an algorithm for the densest subgraph problem under differential privacy, still with edge differential privacy. And now you have a multiplicative factor of 2 approximation with log n additive error. And this uses essentially the same exact ideas because there's this relationship between k-core and densest subgraph, where if you get some approximation for k-core, you can just multiply all those guarantees by 2 and you immediately get that for densest subgraph. So doing that would get you 2 plus eta. If you are just a little bit more clever, you can get a 2 approximation. So this is nice. So previous work on this, this is the best additive error of any differentially private algorithm for densest subgraph. But there are other algorithms that get way better multiplicative error. In fact, Mike
didn't.
He goes by Mike. Okay, Mike recently put a paper on arXiv saying that you don't even need multiplicative approximation. You can get a 1 approximation, and you have log squared additive error. But our additive error is still better than theirs, so it's okay. They didn't steal our result. Another result that is implied by our k-core, I guess, implied in a white box manner, I guess, is that you can get this low out degree orientation thing with some 1 plus eta and log n approximation, additive log n approximation. And this also follows immediately from the k-core decomposition. Previous work is just Lakshman, Chen, and Shangdi's work, and they get a 2 approximation. Now we decrease it to 1 plus eta. And finally, we also showed that all of these results can be implemented in nearly linear time by some clever sampling ideas. So naively doing it, if you see there are like n nodes, and then the do while loop can run n times. So naively, it will run in like n squared polylog n time. And if you do the sampling of the Laplace distributions more cleverly, then you're actually able to implement it in near linear time, which matches the best known for non-private algorithms, which is very nice. Okay, so now I guess I'll be concluding. So some open questions left by our work, and I hope to think about soon when I finally find time. So first, in ongoing work with Chen, we should be able to show that a multiplicative approximation is not necessary for a private k-core. So we can get log n additive error with no multiplicative approximation. So it's known that square root log n error is necessary. And the question here, which hopefully I'll be able to answer affirmatively in a few months, is if log n additive error is necessary. So like the most standard algorithm for, I guess, for outputting these vectors is the Laplace mechanism. And it's pretty clear that if you want to guarantee high probability bounds, you need to incur log n additive error. That's like the extremely hand-wavy intuition for why you think the log n additive error is necessary. And I hope it's true, or else we're gonna have to keep thinking about better approximation algorithms. More generally, I want to see or understand the relationship between parallel and sublinear algorithms and private algorithms. So this relationship was first more formally studied by Lakshman's paper. And they show some, I guess, white box reduction between parallel algorithms and private algorithms. And I hope that this can be explored more. So in ongoing work, we show that parallel algorithms for mask cover can be converted into better, improved, differentially private algorithms for that same problem. So some questions here are, can the sublinear algorithm for correlation clustering by Separasadi and Chen Wang be used to, or be adapted to guarantee differential privacy and with better approximation error?
Can you tell us what max cover is?
Max cover, okay. So in max cover, you have a set system, you have a universe, let's say 1 through n, and you have a collection of subsets of that universe, and you want to choose, and you're also given an integer k, and you want to choose the k sets so that your the number of elements you cover is maximized. And in differential privacy, the elements are the ones that are private. So basically, an element can be added or removed from the set, and you want to be able to choose the sets without using too much information about the existence of a single element in the set. The final thing that I hope to do within the next, say, 3-5 years is to answer the question, can LPs be solved privately in some sense? So there's already some work on this, but basically the additive error will be completely awful. So the previous work on this was published in ICALC 2014. And since then, not a single person has used their algorithm. No offense to the authors, they're really famous, but not a single person has used their algorithms to give like some approximation algorithm for a combinatorial optimization problem. I think we all know how good LPs are. So surely LPs should be the answer to giving a framework for differentially private approximation algorithms. We just need to think really hard. And I'm hoping that some ideas from these parallel LP solvers will be able to do that for us. And
So by parallel LP solvers, you mean multiplicative weight update methods or interior point methods, or?
yeah, more clever than just the PST framework, I think will be needed, but yeah, in general, I'm thinking about the multiplicative weights update method.
So I'm sorry, what does it mean to privately solve an LP?
Okay, great. So in an LP, right, I think the nicest definition will probably be this. You have you have the objective, right? Let's say that's private, and you have a set of constraints, and some of those constraints are private. Wait, did I say the objective is public or private?
Private.
I meant public. Okay. The objective is public, the constraints are private, and the goal of privately solving, so one constraint can be added or removed. And the goal, so you clearly can't satisfy all the constraints. But the goal will be to solve the LP with, let's say, close to opt. But you will violate some of the constraints. And the goal is to bound the number of constraints that you violate. And yeah, the previous thing showed, like in the example of the set cover LP, that the number of constraints they violate is like opt squared times log n. So like opt squared, if opt is small, this is decent, but opt squared is not an ideal thing to exist. So yeah, the hope is that you can have something that is independent of opt. Yeah, thanks. Is anyone going to clap? Thanks.
We have a big slide that says, thank you. You know what it's like.
Next time, I'll keep that in mind.
These mornings, it looks like for me, you need an audio saying wake up also.
Yeah, it's been a tough week. It's gonna be a tough 2 weeks after this too. Yeah. Any questions? Or can I go?
Yeah, so what can you say about, so of course, sublinear algorithms, at least from the viewpoint of lower bounds, are connected to communication complexity also. So are there relations, maybe lower bound relations between communication complexity and differential privacy?
For sublinear algorithms, the lower bounds, their relation to communication complexity is with the constraint that is due to the constraint of linearity, or
the space is limited, yeah.
But for differential privacy, at least right now, I don't care at all about if the things run in sublinear time or space.
No. What I mean is, can communication complexity lower bounds, just like they can be used for sublinear lower bounds, can they be used for DP lower bounds as well?
Okay. So I don't know yet, but I know that, okay, so I think Greg Baldwin and his PhD student Gary had this lower bound related to hop sets, which is only like marginally related here. So they had this lower bound related to hop sets. And then some people at Rutgers like took their idea about the lower bounds in hop sets, and they translated this to lower bound for differential private all pair shortest paths. So right now, not much is known, but like this example might show that there's hope about showing that there's a relationship between the lower bounds as well. Yeah, but it's not clear, and we should figure it out.
So one other interesting direction has been machine time-space trade-offs at, for machine learning by Ran Raz and his students.
Who?
Ran Raz and his students, Ran Raz at Princeton,
Mhm.
students. Very interesting stuff. So, not time-space, memory samples trade-offs, I think.
Mhm.
Basically, if the memory of your machine learning algorithm is small for learning a linear separator or something, then the number of samples has to be large, something like that. I'm just
Mhm.
wondering if for DP, there's a growing set of trade-offs also, or not yet.
I feel like for DP, time-space trade-off, memory space trade-offs. I feel like we're not at the point yet where we are caring about memory. We can't even like give good algorithms or give good mechanisms for problems yet. So we want to first like figure, like even in classical algorithms, we first like figured out what's optimal, and then they saw that there wasn't any work left, and then they started adding all these constraints on sublinearities and streaming and all that stuff. So I think at least in DP, we're still in that first phase.
So could that imply that maybe the DP constraint is too, in general, is too rigid?
Yes, definitely. So yeah, for a lot of problems like set cover, the privacy is just impossible. So as a result, we have to like be clever and define a bunch of like maybe pseudo approximations. Let's say we guarantee approximation with respect to the true set cover, but we only output a partial set cover. And yeah, I'm exploring some of these ideas with Mike right now.
With Mike? Oh, okay. Mhm.
Yeah.
Also, Anil, you're working with Anil as well, right? That's great. Yeah.
Yeah. So yeah, we'll have to be clever with our definitions. But in a lot of these things, DP just means that you can't do anything.
The other thing is in the definition, the way you showed the definition, the probability that A of G equals Y, right? Very often, maybe the user doesn't care about large regimes of Y, right? You only care if, for example, if you're outputting some sensitive thing about, how many people died from COVID in a county or something, right? Maybe there is only some part of the distribution that is sensitive, right? So I wonder if there is one, I've just idly wondered about it. I've not worked on it, but are there meaningful restrictions of DP like this that let you give interesting algorithms?
I don't know. Okay, wait. Sorry, can you define the meaningful?
So
again?
yeah, so in your definition, A of G equals Y versus A of G prime equals Y, right? Maybe somebody who's trying to get some privacy leaked is only interested in some narrow range of values of Y, right? For example, if I don't have this well formed, but that's something I've been sort of idly wondering about. So does it leak too much information to say, if you look at, say, deaths from COVID or things like that, are there regimes where, if you say 10,000 deaths, does it, maybe some numbers are not surprising at all, so we don't care about this, right? It's the surprising parts of the distribution maybe that we should care about.
Sure.
It's an ill-formed question, but for folks like you who may work on DP to think about.
Yeah. Here's one thing. In some survey, I don't know, sometime in the past 2 years, I can't remember, they mentioned that there are like 250 new definitions of variance of DP.
Literally 250.
250. And I would guess that maybe your definition already exists in one of those 250. But if not, we can make it 251.
Okay, I'm glad it's not 250 over epsilon.
Thanks, guys.